Thank you guys for clicking on my video. This is the final video that I'll be making for this Physics 1 class. This is the solved or my solved answers for the final practice exam. In this practice exam, we covered topics like kinematics, forces at angles, forces on inclines, projectile motion, work and energy, and rotational motion and torque. We did not in this practice exam we did not cover um momentum or collisions or resistive forces or fluid mechanics, but I cannot guarantee that those will not show up on the exam. So please um do not watch my video thinking that it's all you need, because there might be some questions, some of those topics on the exam. But anyways, also these are my answers. There was no like answer key for this one, so I could be wrong on some of these, although I hope I am not, but I could be. So if you guys notice a mistake or if you guys get a different answer, please let me know in the comments and we can check answers, or I can check my answers and I'll fix it as quickly as I can so that other people do not follow in my mistakes. But other than that, please enjoy the video, and I hope you guys do good on this final exam, because yeah, I just hope you do. The first problem says that an object's position as a function of time is given by x sub t equals 1.7 t cubed minus 2.5 t squared plus 2t plus 3. And this position is in meters, so it has units of meters. So part A is asking us, what is the object's average velocity between when the time equals 0 seconds and when the time equals 11 seconds. So to get the average velocity of this object, we're gonna use this equation, which is the velocity average is going to be equal to the change in position over the change in time, just like that. And we're going to go ahead and expand this. This is going to be the final position minus the initial position all over the final time minus the initial time. Expanding even more, since we have a position function, we could find these x finals and x initials. That's going to be x. Our final position is going to be when the time is equal to 11. So it's going to be x of 11. And then our initial position is going to be when our time is equal to 0. So x sub 0. Divided by time final minus time initial. Time final is 11 seconds. And then time initial is 0 seconds. So we simplify. Finally, we get x of 11 minus x of 0 all over 11 seconds, and these are in units of meters. So let's just go ahead and evaluate x at 11 and x at 0. So x at 11 would be 1.7 plugging the 11 cubed minus 2.5 plugging the 11 squared plus 2 plugging the 11 plus 3. And then x at 0 would be 1.7 plugging 0 cubed minus 2.5 plugging 0 squared plus 2 plugging 0 plus 3. And evaluating x at 11 will give you an answer of 1985.2, I believe. And this is in units of meters, so we just write meters right here. And then evaluating x at 0 is going to give you 3. So now we plug in these values back in over here, and we get that it's going to be 1985.2 meters minus 3 meters all over our 11 seconds. This will get you a final answer of 180.8. 5.2. Top is meters, bottom is seconds, meters per second. Part B says, what is the object's instantaneous velocity at time equals 11 seconds? So the instantaneous velocity, to get the instantaneous velocity, since we have this position function right here, all we're going to do is we're going to take the derivative of the position function to get our velocity function and then just evaluate our velocity function at the given time. So the velocity function, b of t, is going to be equal to the first derivative of the position function, which is equal to 3 times 1.7 is, what is that, 5.1 t squared minus, not 2.5, but 2 times 2.5 is 5. So that's 5t plus 2 by the power rule. Let me just make sure I did that right. So I did. Now we're just evaluating this. And this new one, now since we're talking about velocity, this has units of meters per second. Now we're just going to evaluate it when the time is equal to 11. So same thing that we did over here, we just plug in 11. So V of 11 is going to be equal to 5.1 plug in 11 squared minus 5 plug in 11 plus 2. And that'll give you an answer of 564.1 meters per second. So it's traveling 564.1 meters per second when the time is equal to 11 seconds. And when between the times of 0 and 11, the average velocity is 180.2 meters per second. All right, now for part C, it says, what is the object's average acceleration between time equals 0 seconds and time equals 11 seconds? This one is very similar to the velocity one. We're just changing, I literally just changed one word. So it's going to be the exact same steps. Well, not the exact same, but the exact same approach. So for this one, the average acceleration is going to be equal to the change in velocity over the change in time. So then that's going to be velocity final minus velocity initial all over time final minus time initial, which, since we just found a function for the velocity, which is this one right here, we'll just use that. So this is going to be, we're going to evaluate V at 11 minus V at 0 all over the 11 minus 0, because this is our final time and this is our initial time. And we can simplify this. We have V of 11 minus V of 0 all over 11. This is seconds. This is meters per second. Now let's just go ahead and evaluate. Since we already have V of 11 right here, we don't need to evaluate it again. So we have 564.1 meters per second minus V of 0. V of 0, we're going to plug in 0 onto our function. So we have into our velocity function. So we have 5.1 plug in 0 squared minus 5 plug in 0 plus 2. So it's just, this will turn into a 0. This turns into a 0. You're just left with this 2. So it's just minus 2. And I should have not, just rewrite it over here. So now this, plugging in our values for V11, V0, it's going to become 564.1 meters per second minus 2 meters per second all over 11 seconds. That'll give you an answer for the average acceleration of 51.1 meters per second squared. Moving on to problem number 2, it says that an object that is initially traveling with the velocity of 20 meters per second in the I direction is subject to a constant acceleration at time equals 0. Part A says that the object moves a distance of 45 meters in the x direction over a time of 10 seconds. What is the constant acceleration of the object over that time? So the I direction and the x direction are the same direction. So I just want to throw that out there. Now, before we start this problem, let's just write down everything that we know. So we know that it's initially traveling with the velocity of 20 meters per second. So velocity initial then is equal to 20 meters per second. And it says that it moves a distance of 45 meters. So then delta x is equal to that 45 meters. And over a time of 10 seconds. So our time is going to be equal to 10 seconds. And it's asking, what is the constant acceleration? So it's asking about the acceleration. What is the acceleration? So we have these three values. We don't have this one. And we also don't have velocity final, but we're not worried about it. We can solve with just these three values. We can solve for this with just these three values. So now we're going to use a kinematic equation. So we're going to use the kinematic equation that does not have velocity final, which is going to be this one. So it's going to be delta x equals velocity initial multiplied by the time plus 1/2 at squared. Now, since we're solving for acceleration, we're just going to go ahead and isolate for acceleration. So let's get rid of these constants right here first. So we're going to do minus VIT minus VIT. So now we have delta x minus velocity initial multiplied by t equals 1/2 at squared. Now, before I do that, I need to explain myself. So now I'm going to get rid of this 1/2 and this t squared both together. So I'm going to do 1/2 divided by 1/2 and divided by t squared. Just like that. Got to do it to this side as well. Divided by 1/2 and t squared. So now we have an answer of a equals delta x minus vi multiplied by t all over 1/2 t squared. Plugging in my values, I'll get for delta x, it's going to be 45 meters minus velocity initial, which is 20. And then the time, which is 10 seconds, all over 1/2. And then our time squared, which is 10 seconds. For a final answer, this is equal to acceleration is going to be, this is equal to our acceleration, which is then equal to a final answer of negative 3.1 meters per second. Meters per second squared, since it is acceleration. For problem letter B, it says, assuming the constant acceleration from part A, what amount of time will it take for the object to obtain a velocity of 3.5 meters per second in the I direction? Again, I is just the same as x. So let's first of all, let's just write down everything we know. We're using the acceleration from part A. So then A is equal to negative 3.1 meters per second squared. And then right here it's asking for time. So that's what we're going to be solving for. Time equals something that we don't know. And then it says the final velocity. What time will it take to obtain this velocity? So this is going to be our final velocity. So velocity final is equal to 3.50 meters per second. And we are also told in the beginning of the problem that the initial velocity is 20 meters per second. So we also have that. Velocity initial equals 20 meters per second. Now we can go ahead. We have these three variables. We're missing one. Well, we're missing two, but we're only solving for this one right now. So we don't care about displacement in this case. For this one, we're going to use the kinematic equation. Velocity final is equal to velocity initial plus acceleration multiplied by time. We have this, we have this, we have this, we don't have this. That's what we're looking for. So let's go ahead and isolate that t. Subtract by vi. Subtract by vi. Now we have vf minus vi equals at. Isolate that t divided by a. Divide this side by a. Then the time is equal to v final minus v initial all over acceleration. which plugging in your values, you get V final is equal to 3.5 meters per second minus velocity initial, which is 20 meters per second, all over the acceleration, which is negative 3.1 meters per second squared. This will get you an answer for time is equal to, an answer of time is equal to 5.32 seconds. So it reaches this velocity at 5.32 seconds. All right, moving on to problem number 3. It says a projectile is launched off a 25-meter high cliff with an initial velocity of 15 meters per second in a direction that makes a 35-degree angle with the horizontal. Part A is asking us what is the object's total displacement in the x direction upon reaching the ground. So in order to find the displacement in the x direction, we're going to use this equation where delta x is equal to the velocity in the x multiplied by the time. It's that simple, but it's not that simple because this velocity x we could solve out. This delta x is what we're looking for, and we're just missing that time, but the time is not going to be that easy to find, but we can't find it. We're going to find the time using our values, our y values, if that's not the right way to say it, but you guys will see. Okay, so first of all, let's split up this velocity. So let's get our Vx and then, well, better on just Vx actually, and then Viy, because I just put Vx because the velocity in the x direction is always the same. The y will have an initial and a final, which means that the velocity will change throughout. So to get the velocity in the x direction, we're going to do the velocity, which is 15, multiplied by the cosine of the angle that it's being that they gave us, which is 35, equal to something. And then for the y, it's going to be 15, the sine of that angle. For the x direction, we get 12.287 meters per second, and for the y direction, we get 8.6036 meters per second. Now, it's asking upon reaching the ground. So this object, so let's say it's like there's a cliff like right here. This object is gonna go all the way up and then down like that. So if we're gonna solve for time using our y values, then we have velocity initial in the y, which is equal to that 8.6036 meters per second. Our acceleration is equal to g, which is negative 9.8 meters per second squared. And then our displacement, since it goes from here to here, and we know that the cliff is 25 meters tall, it's going to be traveling down. So it's going to be negative. So delta y is negative 25.0 meters, just like that. And now we're just going to solve for time. We're going to solve for time using our equation delta y equals vi y multiplied by time plus acceleration, not plus 1/2 acceleration, t squared. And as you can see right here, we have a quadratic equation because our missing variable is t. Well, we don't have a quadratic equation yet, but let's make it into a quadratic equation by taking away this delta y, putting it over here. Now we have a quadratic equation. 0 equals, I'm going to rearrange here, so I'm going to have 1/2 at squared plus viy minus delta y. Plugging in for all of my values, I have 1/2 9.8, negative 9.8 t squared plus v initial y, which is v initial is 8.6036. 8.6036 minus delta y, which is negative 25, but I have two negatives, so that's going to make it a positive, so I have plus 25.0 meters. Let me go ahead and simplify this right here. I forgot about that t. VI t. Just be a t right there and a t right there. So then that 0 equals negative 4.9 t squared plus 8.6036 t plus 25.0. I'm going to keep the units out for right now. So I erase this. Now we have a quadratic equation. This is my A, this is my B, and this is my C. I don't want to write down there, so I'm going to use this space now. I'm not going to show how to solve for the but you just plug this into a quadratic equation, and one answer is going to be negative, the other answer is going to be positive, and the positive answer, well, actually, I'm not even going to use it, but the positive answer, which is the right answer because time can only be positive, is going to be 3.3012 seconds. Let me make sure I did this correct. Yes, I did. That's going to be your time right there. And actually, never mind, I take that back. We are going to use this. So now that we have our time and we have our velocity in the x direction, we can find the displacement. So now we have that the displacement in the x is equal to 3.3012 seconds multiplied by the velocity in the x, which doesn't change, and it's 12.287 meters per second. So then our displacement is equal to an answer of 40.6 meters. So that means that this object, like there's somebody throwing it, and it's this displacement from there, or not from there, but like from there, I guess, from there to the part that it falls, this horizontal displacement is equal to 40.6 meters. Now moving on to the next one. I'm gonna erase this answer. Moving on to the next one, that's part B says, what is the magnitude and direction of the object's velocity when the time is equal to 3 seconds? So to get the magnitude and direction of the object's velocity, we are gonna have to take the square root of the velocity in the x squared plus the velocity in the y squared. That's to get the magnitude. Okay, so let's go ahead and do that. Again, the velocity in the x doesn't change. So we have this. Now we just need to solve for the final in the y. So we have the velocity initial in the y is equal to 8.6036 meters per second. We know that the acceleration is equal to g, which is negative 9.8 meters per second. And then the velocity final is what we're trying to find. And we're given a time of 3 seconds here, so time equals 3 seconds. Solving for this one, we will use this equation right here. So VFY equals VIY plus AT. And this is already isolated for VFY, which we're looking for. So let's just go ahead and plug in everything that we know. VFY is going to be equal to VIY, which is this 8.6036. I'm going to keep the units out, plus the acceleration, which is negative 9.8, multiplied by the time, which is 3. You should get an answer of VFY is equal to negative 20.796 meters per second. Now to get the magnitude, we just take the square root of this squared and this squared. So the magnitude, which we'll call V, is then equal to the square root of this one squared. So it's going to be 12.287 squared, again, I'm keeping the units down just to make this faster, plus negative 20.796 squared, and you get an answer for the magnitude that is equal to 24.154 meters per second, of course. Now, to get the direction, which is the angle, we are going to take our angle theta is going to be equal to the inverse tangent of the y velocity over the x velocity, if I am not mistaken. So now, plugging in our values, we get tan inverse of the y, which was this one, negative 20.796, all over the x, which is that one over there, which is 12.287. Plugging that into the calculator, you get that the angle is equal to negative 59.4, and that, of course, will be below the horizontal. For this one, negative 59.4 is the right answer. However, whenever you're working with the tan function, this tan inverse function, you got to be careful because sometimes it will give you the wrong answer and you're going to have to add 180. So just be careful. For this one, it is negative 59.4 though. Anyways, that is how you do part 3. Problem number 3, part A and B. Next up, we have problem number 4, which says a 1.5 kilogram mass is initially at rest on a horizontal surface. An applied force of 25 newtons at an angle of negative 35 degrees relative to the positive x direction acts on the mass. Part A says, what is the acceleration of the mass if the system is frictionless? So the first thing that you want to do whenever you're working with forces, or the first thing that I do, is I always write these two equations. So the sum of all the forces is going to be equal to the mass times the acceleration, which is just Newton's second law. And then the sum of all the forces is also equal to all the forces, all the individual forces that I have present, or at least the ones that are actually going to be making this object accelerate. In this case, we only have one force acting, or one force that's actually going to make this object accelerate, because the other forces are going to cancel out, and we say that we are told that the system is frictionless, so we don't have friction. In this case, our only force that's actually going to accelerate this object is the applied force in the x direction, which we can write as the 25 newtons multiplied by the cosine of negative 35 degrees, which is the angle that this applied force is acting at. And then plugging this into your calculator, you'll get that that is equal to 20.478 newtons. Now that you have this and you have this, you can set these two equations, or this value and this equal to each other, since we're trying to find acceleration. So we have 20.478 newtons equals the mass times the acceleration. Now we just isolate for acceleration. So you divide by the mass, then your acceleration is just equal to this 20.478 newtons over the mass, which is 1.5 kilograms. So for A, or just plug this into your calculator and you'll get that the acceleration of this mass, if this system is frictionless, will be 13.652, but we'll just say 7. Well, I'll just say 7 because I'll round. 13.7 meters per second squared. Now, part B says if friction acts and the coefficient of mu k is 0.575, what is the acceleration of the mass? So now it's basically the same approach, but now we have friction. Yeah, so again, I'm gonna start it the same way. I'm gonna write out Newton's second law to begin. And then I'm going to write down all the forces that I have present here. So in this case, I'm going to have the applied force in the x direction, and I'm going to have the force of kinetic friction. I'm going to write this in a lowercase f. Now I'm going to take into account the direction of these. So this is going to turn into the sum of all the forces is equal to the force applied in the x minus the force of friction, because friction is going to be trying to stop this object. So it's giving like a negative force. I think that's how you say it. So now we have this. Now, again, if friction acts, we're looking for acceleration again. So now I'm going to go ahead and set these equal to each other. So then I have the force applied in the x minus the force of kinetic friction equals the mass times the acceleration. Acceleration is right there. Just going to go ahead and isolate it by dividing by m to get rid of that m by the mass. This is then going to turn into the acceleration of the object is equal to the force applied in the x minus the force of kinetic friction all over the mass of the object. Now, this is when it gets a little bit tricky. Force applied in the x, we already calculated that to be 20.478. However, the force of the kinetic friction is not just mg times mu, because this applied force is acting at an angle, so it's also giving it's also making this object, like, I'd say not heavier, but it's making, I guess you could say heavier. It's making the object heavier. So we're going to have to take that into account where we calculate the normal force right here. So right down here. So my force of kinetic friction is then equal to, usually we just have the normal force multiplied by mu k or mu s, whatever you're working with. In this case, in most cases, n is just equal to mg. In this case, it's going to be the force of kinetic friction equals mg, which is the normal force just by the object alone. And then I'm going to do minus the applied force, or the y component of the applied force, which is going to be fay, and then that multiplied by mu k. Now here we can solve out for fay. So then the force of kinetic friction is then equal to mg minus fay is just going to be 25 multiplied by the sine of the angle that this force is acting at. So it's going to be 25 newtons multiplied by the sine of negative 35 degrees, all multiplied by the coefficient of kinetic friction. Plugging in our values here, the force of kinetic friction is equal to the mass, which is 1.5, multiplied by g, which is gravity, minus 25 newtons, sine of that angle, which is negative 35 degrees, all multiplied by the coefficient of kinetic friction, which is 0.575. And I should have calculated this value out. Actually, I did right here. This value is equal to 16.697 newtons. Excellent. So that is the force of the kinetic friction. Now we already calculated the force of the applied force in the x direction, which is this one, and we know the mass. So now let's just go ahead and plug in all our values into this and get our acceleration. I'm going to do it over here because I don't want to do it down there. So we have that the acceleration, do it way over here. The acceleration is equal to the force applied in the x, which is 20.478 newtons, minus the force of kinetic friction, which is down here. We just solved for it, 16.697 newtons, all over the mass of the object, which is 1.5 kilograms. Plugging that into your calculator, you'll get an answer of, rounding, you'll get an answer of 2.52 meters per second squared. And I forgot to mention that both of these are in the positive x direction. So let's say we have an object. Let's say the object is like right here, and then the force, like, I guess somebody was pushing on it like this. I guess this object would then start accelerating this way in the positive x direction. But yeah, that's the acceleration with friction and without friction. The next problem says that a 3 kilogram mass is initially at rest at the bottom of an incline that makes an angle of 40 degrees. An applied force begins acting on the mass with a constant force of 25 newtons directed up the incline, parallel to the incline. Part A is asking us what is the acceleration of the mass if the system is frictionless. So just like the last problem, the first two things that I'm gonna do is I'm gonna write down Newton's second law, which is the sum of all the forces equals to the mass times the acceleration. And I'm going to write that the sum of all the forces is also equal to all the forces that I have present. In this case, since this system is frictions, in this part it's frictionless, the only forces that I'm going to have is this 25 newtons that's applied, and of course the force of gravity that's going to be pulling this object down. So then I have the force applied plus the force of gravity. And if I take the directions of these forces into account, then I'll have that the sum of all the forces is equal to the the applied force minus the force of gravity. Now I can set, since both of these are equal to the sum of all the forces, this one and this one are equal to the sum of all the forces, I'll set these equal to each other. So then I have the mass times the acceleration is equal to the force applied minus the force of gravity. Since I want to get acceleration, I'm looking for acceleration. I'm going to divide by m to isolate a. And then I get my answer that a, the acceleration, is equal to the force applied minus the force done by gravity over the mass of the object. Now I just need to plug in my values. So I need to plug in my values, but first of all, we need to find what Fg is. Fg in this case, since it's on an incline, Fg is going to be equal to mg sine of theta. And this theta is going to be the angle of the incline. So then I have that Fg is equal to the mass, which is 3 kilograms, multiplied by g, which is 9.8 meters per second squared, multiplied by the sine of theta, which in this case is 40 degrees. This is going to give me an answer for Fg of 18.897 newtons. Now I'm going to plug in this value here, and this value here. So then I'll get that the acceleration is equal to the 25 newtons done by the applied force minus the 18.897 newtons done by gravity, all over the mass, which is 3 kilograms. And this will give me an answer for acceleration of 2.03 meters per second squared up the incline. And 2.03 is rounding. The exact number is something else, but I'm rounding. So that is without friction, right? Yeah, without friction. Now for part B, it says if the system is not frictionless and the acceleration of the mass is measured to be 0.45 meters per second squared up the incline, what must the coefficient of kinetic friction be? So now we're looking for the coefficient of kinetic friction. I'm going to start it the same way. I'm going to write Newton's second law. So the sum of all my forces is equal to the mass times the acceleration, and then the sum of all the forces is equal to all the forces that I have acting. In this case, we have the applied force, and we have the force of gravity, and now we have the force of kinetic friction. Taking in the direction of these into account, I'll have that the sum of all the forces is equal to the force applied minus the force of gravity, because gravity is going to be pulling my object down, and minus the force of kinetic friction, because kinetic friction is going to be opposing my applied force. It's going to be trying to stop my object. So now I'm going to set this equal to this one. So then I'll have the mass times the acceleration is equal to the applied force minus the force of gravity minus the force of kinetic friction. Now I'm being asked to find the coefficient of kinetic friction, which is going to be found right here. So I got to get rid of this one, and I got to get rid of this one, and then I got to get rid of some other stuff right here. But first, let's just get rid of these two right here. So to get rid of these, I'll do minus FA, and then I'll do plus FG. And then I gotta do the same on this side, so minus FA and then plus FG. So then I'll have that negative FK is equal to MA minus FA plus FG. Now I'm gonna get rid of this negative, so I'll divide by negative 1. Negative 1. Now I have FK is equal to negative MA plus FA, distributing that negative, minus FG. Now I'm going to go ahead and expand this FK. FK is going to be equal to the normal force multiplied by mu K, which in this case, our normal force is going to be equal to mg cosine of theta. And then, of course, multiplied by mu K, which is just mu K like that. Now, this is the force of kinetic friction. So now I'm going to set this equal to this that I have right here. So negative MA plus FA minus FG. Now to finally get this mu K by itself, I'm going to divide by mg cosine of theta. Divided by mg cosine of theta. Divided by mg cosine of theta on this side as well. And now I get my answer, or my formula for my answer. Now I just got to plug in everything. Now I just have to plug in everything. So then I have mu K is equal to negative MA, which M is equal to 3 kilograms, and then A is equal to 0.45 meters per second squared, plus the applied force, which is the 25 newtons that I got from right there, minus FG. FG we found over here to be 18.897. 18.897 newtons. All of this over mg cosine of theta. So mg again, 3 kilograms multiplied by 0. Not that. Multiplied by gravity, which is 9.8 meters per second squared, multiplied by the cosine of theta, which in this case is going to be that 40 degrees. Plugging that into your calculator, you get an answer of, so we'll get that mu K is equal to rounding, you get 0.211. Next problem says that a mass of 0.75 kilograms is initially at rest on a horizontal surface when it is acted upon by a constant applied force in the positive x direction. The mass undergoes a displacement of 5 meters in the positive x direction, obtaining a speed of 15 meters per second over that distance. Mu k between the object and surface is 0.4. Part A is asking us what is the net work done on the mass over the 5-meter distance. The net work done on the mass. Okay. So to calculate the net work done on the mass for this part, we're just going to use the work energy theorem, which says that the sum of all the work is equal to the change in kinetic energy. And that's pretty much it. It's that simple. So the sum of all the work, expanding the change in kinetic energy, would be 1/2 mb final squared minus 1/2 mb initial squared. And since it says it's initially at rest, the velocity initial will be 0, which will make this entire thing 0. So we could just cross this entire thing out. Then we are just left with the sum of all the work is equal to 1/2 mb final squared. And now we could just plug in all of our values because we know all of this to get the sum of all the works. Sum of all the work. So then the sum of all the work would be 1/2 the mass, which is that 0.75 kilograms, multiplied by the final velocity squared, which the final velocity is 15 meters per second. Squared. And you'll get an answer that the sum of all the work, or the net work done on the mass over this 5-meter distance, rounding, you get 84.4 joules. Now for part B, it's asking what amount of work is done by the applied force over the 5-meter distance. So the sum of all of our works, the sum of the work, you can either use this, sum of all the work is equal to the change in kinetic energy, and you can also use this, that the sum of all the work is equal to the work done by the conservative forces minus the work done by the non-conservative forces. I think it's a plus. Okay, so now, since we don't have any conservative forces, in this case we have the applied force and we have the force of friction, we can just cross that out. So then the sum of all the work is just going to be equal to the work done by the non-conservative forces. And the non-conservative forces in this case are if we expand this, it's going to be the work done by the force of applied, the applied force, and then taking the direction into the account, or I'll do that later. So I'll just do plus, and then the work done by the force of kinetic friction. Now, it's asking what amount of work is done by the applied force. So we're trying to solve for this applied force right here. So let's isolate it. We'll do minus the work done by kinetic friction minus the work done by kinetic friction. So now we have that these, not the sum of all the works, but the work done by the applied force is equal to the sum of all the works minus the work done by the force of kinetic friction. And we know that the sum of all the works is equal to 84.4. Well, to be exact, it's going to be 84.375. So I'll write that over here. 84.375 joules, because I want to be exact as possible. So now we're just going to go ahead and solve for this. We already know this, and we can solve for the work done by the force of kinetic friction. So the work done by the force of kinetic friction is going to be equal to the force of kinetic friction, which is Fk, multiplied by the displacement. Expanding that, you get that the work done by the force of kinetic friction is going to be equal to mg multiplied by mu k multiplied by delta x. Plugging in all of our values, we get that the work done by the force of kinetic friction is equal to the mass, which is 0.75 kilograms, multiplied by the force of gravity, the acceleration due to gravity, which is 9.8 meters per second squared, multiplied by mu k, which is 0.4, multiplied by the displacement, which is 5 meters. I also forgot to mention that this force is going to be acting, the work that friction does is going to be negative, because the work that friction does is like opposing the motion, so it's trying to slow down this object. So really, I should have put the cosine of 180, I think it is, and it would have made this whole thing negative, but I'll just throw in the negative at the end. So the work done by the force of kinetic friction is then equal to an answer of 14.7. And again, this force of kinetic friction is the work done by the kinetic friction is going to be opposing the work done by the applied force. So this is going to be negative. So just throw in a negative right there. Mathematically, you're supposed to get the force, to get the work, you're supposed to do the cosine and then whatever angle it's acting at, which in this case is 180. So I could just go ahead and throw that in there. Cosine of 180. Cosine of 180. Cosine of 180 is just negative 1. It would have made this 14.7, negative 14.7. Now you can go ahead and plug that in to here. Plug that into here, and you'll get your answer for the work done by the applied force. So then the work done by the applied force is then equal to 84.375 joules minus negative 14.7 joules. I forgot to mention that is in joules. Plugging that into the calculator, this will become a positive, so it's 84 plus this 14. So then your work done by the applied force is then equal to an answer of, well, when you round, you get 99.1 joules. The next problem number 7, says that a 0.65 kilogram mass is held at rest against a linear spring that is compressed by 0.7 meters. The spring force pushes on the mass in the positive x direction, and the mass is on the horizontal surface. If the mass leaves the spring with the speed of, part A says that if the mass leaves the spring with the speed of 10 meters per second and the surface is frictionless, what is the spring constant of the spring? So in part A, the only force that is going to be acting on this mass is going to be the spring force, or the only force that's going to be accelerating it is going to be the spring force. And since the spring force is a conservative force, we can say that the way that I'm going to say it is that the change in the object's kinetic energy is going to be equal to negative the change, or the change in the kinetic energy of the system is going to be equal to the change in the kinetic energy, not the kinetic energy, the potential energy of the spring specifically. So I can say this because we only have conservative forces acting on this mass for this part. So now I'm going to expand these. So expanding the change in kinetic energy is going to get me 1/2 mv final squared minus 1/2 mv initial squared equals, I need to take into account that negative, so I'm going to throw in the negative right here. Negative 1/2 kx final squared. And then it would be minus, but since I have that negative, I have to distribute it, so it's going to be plus 1/2 kx initial squared, like that. And since we know that it is held at rest, the initial velocity of this mass is going to be 0. So I can go ahead, and if I were to plug in 0 here, it would make this whole thing 0. So I could just cross that out. This negative will go away as well. And I also know that once the mass leaves the spring is no longer going to be like compressed anymore, so it's not going to be displaced. So I know that the final displacement of this spring is also going to be 0. So this is going to be 0, which makes this entire thing 0, so I could get rid of that as well. So then I'm left with 1/2 mb final squared equals 1/2 kx initial squared. And I have a 1/2 on each side. I could go ahead and cancel these out. Now I have mb final squared equals kx initial squared. And we are being asked, what is the spring constant? Spring constant is right there. So let's just go ahead and isolate it by dividing by xi squared. Divide this side by xi squared as well. Now we get that k is equal to mb final squared all over xi squared, which is then equal to, once I plug in all my values, the mass is equal to 0.65 kilograms, and the speed is equal to 10 meters per second, but we're going to be squaring it, so I'm just going to square it already. It's going to make it 100 meters per second all over the initial compression of the spring, which is 0.07 meters, and this is squared, so we'll square that. And once you plug that into the calculator, you'll get a spring constant of, well, once you round, you'll get, or I got 13,265 Newton meters. All right, and then for part B, it says if the mass leaves the spring with the speed of 10 meters per second and the coefficient of kinetic friction is 0.75, what is the spring constant of the spring? So it's going to be leaving the spring at the same speed, but now we just have friction. So we can't do this because now we have a non-conservative force. So the first thing that I'm going to do is I'm going to write down the work energy theorem, which says that the sum of all the works is equal to the change in kinetic energy. And now I'm going to write down all the works that I have present. So the sum of all my works is going to be equal to my work done by the conservative forces plus the work done by the non-conservative forces. In this case, the work done by the conservative forces will be my spring. The work done by the non-conservative forces is going to be the force done by kinetic friction. Now I'm going to set these two equal to each other because they're equal to the same thing. So the change in kinetic energy is going to be equal to the work done by the conservative forces plus the work done by the non-conservative forces. And I can rename these, I guess, as the change in kinetic energy is equal, my conservative force is the spring force, so I could say the work done by the spring force plus my non-conservative force is the spring force. I mean, not the spring force, the kinetic friction. So I could write it like that. Now I'm being asked for the coefficient of kinetic, not the coefficient of kinetic friction, but the spring constant of the spring, which is going to be found right here. So I'm going to go ahead and isolate that by subtracting the work done by kinetic friction. Now I have that the work done by the spring is equal to the change in kinetic energy minus the work done by the force of kinetic friction. Expanding this work done by the spring, in this case, the work done by the spring is going to be equal to 1/2 kx initial squared. So I can go ahead and plug that in here and then just isolate for k. So now I have 1/2 kx initial squared equals the change in kinetic energy minus the work done by kinetic friction. Now here, I'm going to go ahead and expand these as well. So then I have 1/2 kx initial squared is equal to, we found in the previous part that the change in kinetic energy is just going to be equal to 1/2 mv final squared, because this object starts at rest, so it has no initial velocity, so that cancels out. So I'm going to go ahead and write that already. So I'm just going to go ahead and write that. So mv final squared minus the work done by the force of kinetic friction. The work done by kinetic friction is going to be the force of kinetic friction multiplied by the distance, and the force of kinetic friction is going to be equal to the normal force multiplied by the coefficient, which the normal force is just mg. So I'm going to go ahead and write that already. So I have mg multiplied by the coefficient of friction, which is mu k, multiplied by the distance that it travels, which the distance or the displacement is just going to be the amount that the spring is compressed, which is that 0.07. Or I could have just put delta x, but I guess I could just plug it in already. Now here, I'm just going to go ahead and isolate for that k. So to get rid of this 1/2, I'm going to divide this side by 2, and I'm going to divide this entire side by 2, which is going to get rid of this 1/2, and it's going to put a 2 right in front of there. And then I'm going to divide by this x initial squared. Divide by this x initial squared. So then now my new and final equation is k is equal to mv final squared minus 2 mg multiplied by mu k multiplied by, I'm going to replace it with delta x, just like that. Now all of this is going to be over this x initial squared. Now I can go ahead and plug in all my values. For this one, I'm just going to plug in the numbers, and I'm going to keep them as short as possible because I'm running out of space here. mv final squared is going to be the mass multiplied by the velocity final squared, which is 0.65, multiplied by the velocity squared, which is 10. Where does it say that? Oh, 10. Oh, it says right here as well. 10 squared, which is 100. I'm going to keep the units out. Minus 2 mg, which is 0.65, multiplied by 9.8, multiplied by mu k, which is 0.75, multiplied by the displacement, which is 0.07. That looks very messy, but yeah. All over the initial x, which is how much the spring was initially compressed by, which is that 0.07 meters. So 0.07 squared. That's a square. And then once you plug all that into your calculator, you'll get a final answer. Rounding, you'll get a final answer of 13,401 newtons over meters. This makes sense. This says that it needs to have a stronger spring constant to make this mass go the same speed as when it doesn't have friction. Yeah. You just ruined my whole video. Come, because I'm going to beat you up. The next problem says that a point mass of 0.2 kilograms initially at rest is attached to a string and set into circular motion under a constant angular acceleration of 1.5 radians per second squared. The string has a length of 2.5 meters and is fixed to rotate about its end. Part A is asking us at what time will the angular velocity of the system be 50 radians per second. So the first thing that I'm going to do is I'm going to write down everything that I know. So I know that I'm trying to find the time. So I don't know the time, but I have a question mark there to show that that's what I'm looking for. I know that my omega final has to be this 50.0 radians per second squared. And I know that my omega initial, since this object was initially since this mass was initially at rest, omega initial is going to be 0 radians per second. That's not squared, that's just seconds. And I know that my acceleration, my angular acceleration is 1.5 radians. So then alpha is equal to 1.5 radians per second squared. Here I'm also given the length of the string, but I'm not going to use it for this part. So I'm giving 3 quantities and I'm looking for this one. So the equation that I'm going to use is omega final is equal to omega initial plus alpha multiplied by t. T is right there, so I'm just going to go ahead and isolate for it. Since I know that omega initial is equal to 0 radians per second, I'm just going to go ahead and cross that out right now. So then omega final is equal to alpha multiplied by time. To get rid of this alpha, I'm going to divide by it. So then my time is equal to the omega final all over alpha, which plugging in my quantities, I'll get that omega final is equal to 50. So 50.0 radians per second all over my acceleration, which is 1.5 radians per second squared. Plugging that into my calculator, I'll get a time of 33.3 seconds. And the threes just keep going on forever and ever. So that is my answer for the first part. Answer for this second part is asking what centripetal force must act on the mass after tenfold revolutions. So the equation for centripetal force is this one right here. So the centripetal force is equal to mr omega squared. So now here I'm gonna have to solve. So again, this is the equation that I'm gonna use, but I'm gonna write down everything that I know. So I know that omega initial is equal to this 0 radians per second. I know that alpha is equal to 1.5 radians per second squared. And this time I'm gonna write it on the side though, but I know that the radius is gonna be 2.5. So my radius is 2.5 meters. Omega initial, I have alpha, and I also have delta theta, which is this 10 revolutions. However, in order to be able to use this 10 revolutions with my other equations, I have to convert this to radians. So what I'm going to do is I'm just going to convert this 10 revolutions to radians. And to do that, I'm just going to multiply by 2 pi, which will then get me 20 pi radians. Now I have 1, 2, 3 quantities, and I'm looking for my omega final. I forgot to mention, but that's what I'm looking for. I'm looking for omega final. So to get the omega final, I'm going to be using the equation omega final squared equals omega initial squared plus 2 alpha delta theta. Now here, since we know that omega initial is equal to 0 radians per second, we just go ahead and cross that out already. So then omega final squared is equal to 2 alpha delta theta. Now here I need to isolate this omega final, so I'm going to take the square root of this and square root of this whole thing right here. So now I have that the omega final is equal to the square root of 2 alpha delta theta. Plugging in for all my values here, I'll get that omega final is equal to the square root of 2, and then alpha is known to be this 1.5 radians over second squared. multiplied by delta theta, which we know is 20 pi radians. Now solving for that, I'll get that omega final is going to be equal to 13.729. 13.729 radians per second. Now that I have omega final, I could go ahead and plug it in here, and I have the radius, which is 2.5, and I have the mass, which is 0.2. And yeah, so let's just go ahead and plug it in. So then my centripetal force after 10 revolutions is going to be the mass. So the mass is 0.2 kilograms multiplied by the radius, which is this 2.5 meters, multiplied by omega squared, which is 13.729 radians per second squared. And I'll get a final answer. Once I round, I'll get that the centripetal force is going to be 94.2 newtons. After 10 full revolutions. The next problem says that a 1.5 kilogram solid sphere with the radius of 0.4 meters rolls across a level ground without slipping. It moves forward in a straight line with an initial linear speed of 20 meters per second and is subject to an angular acceleration of negative 2.5 radians per second squared. Part A is asking us how many revolutions will it roll through in coming to a stop. So the first thing that I'm going to do for this problem is I'm going to write down everything that I am given. So I know that, so it says how many revolutions will it roll through in coming to a stop. So I know that the final angular velocity is going to be 0 radians per second. And I know that it has an angular acceleration of negative 2.5. So alpha is equal to negative 2.5 radians per second squared. And it says how many revolutions. So we're looking for delta theta. And it also tells us that the initial linear speed is 20 meters per second. So we know that the initial linear speed is 20 meters per second, but we also know that it has a radius of 0.4 meters. So by using the radius and the linear velocity, we can find the initial angular velocity by this equation. So VI is equal to omega initial multiplied by the radius. So now we're just going to isolate for omega initial. So we divide by R on both sides. And then we get that omega initial is equal to the velocity initial over the radius, which then omega initial is equal to the velocity initial, which is at 20 meters per second all over the radius, which is 0.4, which is then equal to a value of 50 radians per second. And now we can go ahead and write this over here. So then now our omega initial is 50.0 radians per second. Now we have 1, 2, 3 values, and we're looking for this one. So we're going to be using the equation omega final squared is equal to omega initial squared plus 2 alpha delta theta. Our delta theta is right there, so we're going to go ahead and isolate for that. We know that the omega final is going to be equal to 0, so we can go ahead and cancel that out right now. And the first thing that I'm going to do is I'm going to get rid of this constant, so I'm going to subtract by omega initial squared, subtract by omega initial squared. So now I have negative omega initial squared equals 2 alpha delta theta. Finally, isolating for delta theta, I'll divide by 2 alpha. So then delta theta is equal to negative omega initial squared all over 2 alpha. Now that now plugging in my values, I'll get negative 50 radians per second squared all over 2, and then my alpha is equal to that negative 2.5 radians per second squared. And plugging this into my calculator, I'll get that delta theta is equal to 500 radians. But this is 500 radians, but it's asking us for revolutions. So to convert this 500 radians to revolutions, we are just going to divide by 2 pi. And then we'll get a final answer. Rounding, we'll get 59.6 revolutions. So that's how many revolutions it's going to go through in coming to a stop. Now, part B is asking us at what time will the total kinetic energy of the sphere be 100 joules, and the moment of inertia is of this sphere is 2/5 mr squared. So to get the time, we're gonna set up an equation for this. So we know that the total kinetic energy, which I'll call KET, is equal to the linear kinetic energy plus the rotational kinetic energy. So kinetic energy linear plus kinetic energy rotational. I'm going to go ahead. I know kinetic energy total, we're given that it's 100 joules, but I'm not going to write it yet. So I'm going to expand these two right here. Expand these two right here. So now I have that kinetic energy total is equal to kinetic energy linear is going to be 1/2 mv squared plus kinetic energy rotational is going to be 1. Is it 1/2? I don't think it's 1/2. It is 1/2 I omega squared, where omega is omega final, and then the I is, of course, this right here. So now we're going to go ahead and expand this even more since we have these values. Now I'm just going to do this right here. Actually, first, so the way that we're going to find this is we're basically going to find when omega final, because we know, not omega final, but I'm going to change this into linear. So I'm going to get omega in terms of V. So I'm going to do that is KET is equal to 1/2 mv squared plus 1/2, and then I'm going to plug in that I, which is 2/5 mr squared, and then omega, we know that from over here we know that velocity is equal, the linear velocity is going to be equal to omega multiplied by r. So getting omega in terms of V, I'll divided by r. So then omega is equal to V over r, which is the same thing I had over here, so I could have just copied it. But now instead of writing omega, I'm going to write V over r. So I have V over r, and that's squared. So square that. Now I'm going to go ahead and simplify this piece right here. So then I have that the kinetic energy total is equal to 1/2 mv squared plus, this is going to be, what is that, 2/7 mr squared multiplied by v squared over r squared. And as you can see here that this r squared is going to cancel out with this r squared. So then now I just have that the kinetic energy total is going to be equal to 1/2 mv squared plus 2/7 mv squared. Here I can pull out this mv squared, so then I'll have KE total equals mv squared 1/2 plus this 2/7. I can go ahead and simplify this 1/2 plus 2/7. Is that what I did over here? I don't think that's what I did over here. 2/7. That is not 2/7. I messed up over here. 1/2 multiplied by 2/5 is not 2/7, it's 2/10. 2/10. 2/10. 2/10. Now I'm going to go ahead and simplify these. So then to simplify, I'm going to get a common denominator. I'm going to multiply this 1/2 by 5/5, which is then equal to 5/10. And I'm going to do 5/10 plus that 2/10. Now I get 7/10. So then I get that the kinetic energy total is equal to mv squared. Not mv squared. I mean, yeah, mv squared, but I'm going to write this fraction first. So 7/10 mv squared. 7/10 mv squared. And now from here, I'm going to go ahead and isolate this. Not isolate, but solve for v. Well, yeah, isolate and solve for v squared. And then I'll get the velocity that this needs to be, and then once I find the velocity, I can find the time. So here I'm going to divide by 7/10 and divide it by m. So I'm going to divide by 7/10 multiplied by m. Same thing on this side. 7/10 multiplied by m. So then I have that the kinetic energy total is then equal to not the kinetic energy total, but the velocity squared. That the velocity squared is equal to the kinetic energy total all over 7/10 multiplied by m. And then to get rid of that squared, I'm going to take the square root. So then my velocity is going to be equal to the square root of the kinetic energy total all over 7/10 multiplied by the mass. And now here, I can go ahead and plug in my value. So the velocity is equal to the square root of the kinetic energy total, which we are told that it's 100 joules all over 7/10 multiplied by the mass, which is 1.5 kilograms, just like that. And now I'll get that my velocity has to be 9.759 meters per second. That's the linear velocity. And now using this, I'm going to go ahead and solve for the time. Okay, so now that I found the linear velocity when this sphere's total kinetic energy is 100 joules, I can use this to find the time. So I'm going to bring that over here. So the velocity final, that's going to be my final velocity, which is 9.759 meters per second. And I'm told that my initial velocity is this 20 meters. So velocity initial equals 20.0 meters per second. And I know that, okay, so I'm finding my time. I don't know my displacement, but I do know the angular acceleration. And by using that angular acceleration, I can find my linear acceleration. So my linear acceleration is going to be equal to the angular acceleration multiplied by my radius, which is then the acceleration is equal to my angular acceleration alpha, which is negative 2.50 radians per second squared, multiplied by my radius, which is that 0.4. Plugging that into my calculator, that'll give me negative 1.0 meters per second squared. Now I have my acceleration, so my linear acceleration is equal to negative 1 meters per second squared. Now I can solve for my time using this equation. So my velocity final is equal to my velocity initial plus my acceleration multiplied by my time. Now here I'm just going to isolate for time. So I'm going to subtract the velocity initial. So then I have velocity final minus velocity initial is equal to my acceleration multiplied by my time. Isolating for time, all divided by A. I'll get that my time is equal to the velocity final minus the velocity initial all over the acceleration. Plugging in for my values for velocity final, I have this 9.759 meters per second minus this velocity initial, which is 20 meters per second all over my acceleration, which is this -1 meters per second squared. I'll get that my time, or rounding, I'll get that my time is equal to 10.2 meters per second, not meters per second. I get that my time is equal to 10.2 seconds. Okay, so we are at the last problem, and it says that a 0.6 kilogram solid cylinder has a radius of 0.7 meters and is bound to rotate about its center. So we have this cylinder right here, and there are three forces that act on the object as shown below. Force 1, which is this one right here, has a magnitude of 20 newtons at a distance of 0.35 meters, which is this distance right here, from the center at an angle of 110 degrees radially outward. Force 2 has a magnitude of 18 newtons tangentially applied at the outer edge. Force 2 is this one right here, and its radius is just the radius of the cylinder. And then force 3 has a magnitude of 15 newtons at a distance of 0.5 meters from the center at an angle of 35 degrees radially outward. 35 degrees radially outward. That's this one. And then part A is asking us, what is the net torque acting on the cylinder? So like with the net force, the net torque is very similar. So the first thing that I'm going to do is I'm going to write that the sum of all my torques, which is also the net torque, is equal to all the torques that I have acting. So I have torque 1 plus torque 2 plus torque 3. Now I'm just going to go ahead and solve for torque 1, torque 2, and torque 3. Torque is given by force times distance, force times radius times the sine of that angle, or F times R times sine of theta. So we have F times R times sine of theta. So then I'm going to solve for torque 1 is equal to the force, which is this 18 newtons, multiplied by the R, which in this case is just the distance that it's being applied from the middle. So in this case, it's going to be not 18 newtons, but 20 for torque 1. 20 newtons multiplied by this 0.35 multiplied by the sine of the angle that it makes, which is 110. This is going to be equal to 6.5778. 6.5778 Newton meters. And as we can see from this picture right here, since it's pushing like this way, it's going to make this cylinder rotate like this, which is clockwise. So I'm just going to go ahead and write that. I'm just going to draw it like that and write it clockwise. And then for torque 2, same thing. Now we have 18 newtons multiplied by the radius, which in this case it tells us that it's applied at the outer edge, which is right here. So it's just going to be the radius of the cylinder, which is 0.7. Multiplied by the sine of that angle. This makes an angle of 90 degrees, like that. So the sine of 90 degrees, which the sine of 90 degrees is just 1. This is going to then be equal to 12.6 Newton meters. 12.6 Newton meters. And if you can see right here, if we were to apply force down like that, it's going to make this cylinder move like this. So clockwise, again. Clockwise. And now for torque 3, we have 15 newtons. And then the radius is 0.5. And then the sine of the angle is sine of 35. And then this is going to be equal to 4.3018. 4.3018 Newton meters. And as you can see from this drawing, if I were to push down like right there, if I had a circle right here and I was to push down like this, it would make my circle or cylinder start to move like this. So that's counterclockwise. So then that's like that, counterclockwise. Now that I have all of these values, I can go ahead and plug them in to this thing that I have up here. So then the sum of all my torques is going to be equal, and I'm also going to apply also going to take into account the direction. So since I have more clockwise ones, and it's obvious 12 plus 6 is 18, that's more than 4, I'm going to make my clockwise positive and my counterclockwise negative. So then torque 1 will be positive. This is 6.5778. 6.5778 Newton meters, plus this other positive one, which is 12.6 Newton meters, and then minus this one that's negative because it's going the other way, minus 4.3018 Newton meters. And then solving for that, I'll get that the sum of all my torques, or otherwise the net torque, is going to be equal to 14.876 Newton meters, and that is going to be clockwise, or this way, like that. Okay, so now part B says that if the cylinder is initially at rest, what will its rotational kinetic energy be 3 seconds after the forces begin to be applied? Assume that the forces remain acting in their given orientation with respect to the sheet. So these forces are always going to be acting at these angles and at those radiuses. So now, in order to, so first let me write out the kinetic energy, the rotational kinetic energy formula. So the rotational kinetic energy formula is going to be 1/2 I omega squared, specifically omega final squared. So I can solve for I because I'm told that I equals 1/2 mr squared. I know m and I know r. So I can solve for that easily. I just need this omega final squared. So omega final squared is what I'm looking for. It's what I don't know. And we know that this is initially at rest. So we can say that omega initial is 0 radians per second. We are also told that to find the rotational kinetic energy after 3 seconds. So then our time is equal to this 3 seconds. And we are looking for omega final. We don't have alpha, we don't have the rotational acceleration, but we can find it because we know the net torque. So another way to write the net torque would be the net torque is equal to I multiplied by alpha. where I is the moment of inertia, and then alpha was just alpha, which is the rotational acceleration. So we know I, we know the net torque, so let's go ahead and isolate for alpha, divided by size by I. So then we get that alpha is equal to the net torque over the moment of inertia, which is then equal to 14.876 Newton meters all over the moment of inertia, which is 1/2 the mass, which is 0.6 kilograms, multiplied by r squared, where r is the radius of the cylinder, which is this 0.7 meters squared. So then plugging that into your calculator, you'll get that alpha is equal to a value of 101.19 radians. 101.19 radians per second squared. So now we can go ahead and rewrite this over here. So that's 101.19 radians per second squared. Now let's go ahead and solve for omega final. Using this equation, so we have omega final is equal to omega initial plus alpha multiplied by the time. And this is nice because every omega final is already isolated and omega initial is 0, so we can just cross that out. So then we just have that omega final is equal to alpha multiplied by time. Plugging in our values, we get that omega final is equal to this alpha, which is 101.19 radians per second squared, multiplied by the time, which is this 3 seconds. We get that omega final is going to be equal to 303.59 radians per second. 303.59 radians per second. Now that we have omega final, now that we know the omega final at this time, we can now plug this omega final in to this here and solve for the rotational kinetic energy at 3 seconds. So let's just go ahead and do that. So the rotational kinetic energy then, plugging in all my values, is going to be 1/2, and then the moment of inertia is 1/2 again, m, which is 0.6, multiplied by r squared, which is 0.7 squared, multiplied by omega final squared, which is what we just solved, which is this 303.59 radians per second. And plugging all of that into your calculator, you'll get that the rotational kinetic energy at 3 seconds is equal to 6,774 joules.